And to the two kids in the Raymond, Alberta class that were just bobbing along the whole time, thank you very much for that. I always bob along too. It's half the fun. My name is Jesse, everyone. I'm your virtual adventure guide here at Exploring by the Seat of Your Pants, and a huge welcome into today's exciting broadcast. I know we got some new faces in the crowd today, and so if you are new to us, we are all about bringing conservation, adventure, and science into classrooms around the world through over 40 live, free, monthly interactive broadcasts. Every single thing we do goes to our YouTube channel. So after this, if you really love it and you want to show your family and friends tomorrow, or like 4 years from now, you can check it out on the YouTube channel and catch up with Hira then as well. Now, today I'm particularly excited because we are continuing with part 2 of a really spectacular partnership in conjunction with the Institute for Space and Exploration Science at the University of Western Ontario. We did a program with Vanessa Van Decker not long ago. She did an extraordinary program on that YouTube channel I mentioned. Next week, we're getting the chance to hang out with Caitlin Hutton, and don't tell them, I'm particularly excited about today's program because we are joined live by Hira Nadeem, who has packed more into a short career than anyone really ought to. She just finished her master's thesis yesterday, which I know for our grade 5 and 6 kids, you may not understand how crazy that is, but the fact that she's here at all and is sane and is awake and is not like hepped up on coffee is incredible. So Hira, it's so thrilling to have you here today to talk about moon rocks, machine learning, your satellite work, everything you do and more. I think you've probably been to Mars secretly in there somewhere. I don't know. We're going to find out throughout today's broadcast, but if our kids today are fascinated with space, you could not be in a better program. And so without further ado, take us away, Hira.
Awesome. Yeah, thanks so much, Jesse. Yeah, I'm so excited to be here with all of you today. It may seem like I'm much older, but not too long ago I was where a lot of you are sitting and thinking about what I want to do when I grow up. And I will assure you that I still am trying to figure that out. So today I'll talk to you about what I've done in my master's with the Institute for Earth and Space Exploration at Western. And I was very fortunate to work with a really cool company called Mission Control Space Services throughout my master's. So just quickly, who am I? So my name is Hira. I just finished my master's yesterday. I just have a little bit of editing to do, and then it'll be the final submission. But I'm done my degree in electrical and computer engineering with a collaborative specialization in planetary science. So that just means I do engineering and science a little bit. What I do now is that I operate satellites in my job. I moved out to San Francisco about 2 months ago now, and I work as a space systems engineer at a really cool company called Planet. And so we'll talk a little bit about what we do here. But and I also, during my master's, while I was doing, moon rocks, I was also working on a CubeSat project, which is this really small satellite about the size of a loaf of bread, and that will be launching in actually a couple of months. So I'm really excited about that. So this is a little throwback picture of me from the 7th grade. I really thought about it when I was coming to talk to you guys today, because this is maybe what some of you are going through right now, thinking about what you're interested in and what you want to do. So when I was in the 7th grade, I didn't know at all what I was interested in, but I had a really cool 7th grade science teacher who encouraged me to submit something to the science fair. And I thought about, what should I do? And I saw this really cool book called Junk Bots, Bug Bots, and something and beyond. So I picked that up at the bookstore, and inside of it, it told me that I could make a robot from household objects. So that's what I submitted to the science fair. And it kind of got me thinking about, what else can I do? Can I, make robots for Earth? Can I make robots for space? And at this time, I was hearing a lot about the Mars Curiosity rover, about kind of the science that was being done by NASA, and astronauts had been going to the moon over the past couple decades prior. And there was a lot of science and cool stuff. And I thought, maybe I should be an astronaut. Maybe I should go to space and do some cool science. But launching to space is a lot like going on a roller coaster. And I will be honest with you, I'm very afraid of roller coasters. So I thought maybe that's not the career path for me, to go into space and launch on a rocket. That if I can't really go on a roller coaster, I don't know if any of you have been in line at Disney World or Wonderland and been really scared. That was me. So I thought about what was it about these really cool missions going to, sending a rover to Mars or sending astronauts into space? Why was it so exciting to me? And I thought about, the people on the ground who were helping achieve these really, really big and cool goals. And I wanted to be like them. There's this huge team of people from all across the world, different backgrounds, all working together to kind of accomplish this really big feat of space and going into space. And yeah, so I thought about, maybe I want to be in mission control. Maybe I want to be sitting in that room and, be able to jump up and down and get super excited. And so that's kind of what my goal was throughout, going into school, going to university, high school, up until university, and even into my master's, was this idea of, I want to be on a team with a bunch of cool people all trying to achieve the same goal. And so I pursued math and science. I will be honest, I wasn't always the best in school. Tests are kind of hard. And I find that I'm much better in sessions where I'm doing projects rather than tests. So, if you don't like tests, it's okay. I didn't either. And I got through it and just got to persevere. So with a lot of effort, consistent effort, perseverance, I was able to get a degree in engineering in my bachelor's degree at McMaster University. And then after that long journey of school, I thought about, what exactly do I want to do next? Do I want to go into a job, or maybe I should consider, learning something else that could help me on this goal of being in that room in mission control. So I thought about, I have a great background in engineering, but I also want to learn about science, and I want to try to understand how, as an engineer, I can contribute to scientific missions, going off-world, looking back at Earth, things like that. So I decided on going to Western University, the Institute for Earth and Space Exploration, and I was fortunate to have the opportunity to work with some cool scientists, learn from them, and work with this really cool company, Mission Control Space Services. So I'll talk to you a bit about the research I was doing for the past couple of years. But before we get into it, to give you a bit of background on, what I was doing, basically I did a master's studying the moon and trying to develop solutions for assisting lunar robotic missions and planetary scientists with their tasks, looking at things like the moon. So the moon, as you might know when you look up, is our closest neighbor. It's about 385,000 kilometers from Earth. So that's pretty far away, even though it looks like, you could touch it. It's our only natural satellite, and it's the only place that humans have visited outside of Earth so far. So hopefully in the next, decade, we'll see humans go back to the moon, and maybe even Mars. But the moon is an interesting place. It has a very thin atmosphere. So unlike Earth, where we see a lot of, weather, we see earthquakes, we see volcanoes, we see, water and all this stuff that's happening and changing the landscape of the Earth throughout seasons. The moon pretty much stays the same. It has a very thin atmosphere. Not a lot of changes have been happening to it, and it stays pretty much the same since it was formed and kind of settled down. It's pretty much stayed the same. And it's covered in these craters and like little impacts from basically not having an atmosphere. There's not a lot of protection for it. We don't experience any like major impacts or anything. You might see meteorites when they come into the atmosphere, they kind of burn up. On the moon, they actually just land on the surface because there's nothing helping it burn up. So the moon is a really interesting place that has a lot of history embedded within it. And going there and learning about it can help us to learn more about the formation of the moon, but also the formation of our solar system and the Earth itself. So there's a theory about how it was formed. It was basically that a chunk of the Earth broke off in the early formation of the Earth, and that got captured in the gravity of Earth, and it now orbits Earth and kind of stays in its orbit. So in the beginning, the moon was thought to be very active. So it was a hot ball of magma that ended up cooling. So it started to have this rocky surface. And then there was a period of a lot of impacts, a lot of activity in the solar system as a whole, and that kind of cratered the surface and got it all these like cool blemishes that it has now. And then there's theorized to be a period of volcanic activity, which also changed the surface of the moon. and created a lot of the lunar mare, which are kind of the oceans or the deeper crater areas, as well as the highlands, which are kind of like large, like taller areas on the moon. So now the moon is pretty much just covered in lunar dust and craters. So, this is of particular interest to me, is what does this dust mean? Like, what can we learn from this dust, and how can we understand what the moon is, what the early life of the moon was like, and also the early life of the solar system from this moon dust? And can we use this moon dust? Is it useful to us as we further go into space and develop and kind of explore? Can we use this moon dust to help us get further? And what does this moon dust imply for other planets? And can we use this as a place for humans to train when they're going? So during my master's, I took a lot of courses to learn about this, but one of the greatest experiences I had was going into the field and learning about planetary formation. So I got to go to this really cool place called Meteor Crater out in, actually now I'm trying to remember if it was Utah or Arizona, but it was a desert place. So Meteor Crater, I got to go through Arizona and Utah, go to Grand Canyon, and got to see these really cool ways that the Earth has made these cool geologic places. So I learned a lot about how the Earth has been impacted by weathering and by craters and different planetary different things in the solar system to form the amazing surface of the Earth. And so this helped me learn about, what does it look like when rocks have been interacting with a big impact? What kind of different features exist? And so learning about this and being able to touch the sand and think about what this means for the moon was really important. And this is what we do a lot. A lot of planetary scientists will study the Earth and the way that the Earth was formed to understand how other planetary bodies might be similar, or how the different gravity and different environments might be different from the Earth. So it was a really great trip. And I think this was the place where I learned the most, and I got to camp out in the desert for 2 weeks. And yeah, I think it's a great experience if you could ever do that. And as an engineer, not a scientist, this was a very, very big learning experience. So getting into what I looked at on a small scale, I looked at the Lunar Regolith. So Lunar Regolith is basically the lunar sand. So it's a thick layer on the moon of unconsolidated, which means kind of not really compact. It's kind of all spread out, just like if you were going to the beach. That's kind of what the moon's surface is like. It's very loose, kind of, particles of rocks and different things within it. So there's a really thick layer of this on the surface of the moon, and it has a lot of this information. And so there's a lot of different types of particles that exist, but we were really interested in looking at a few types. So rock is one of them. Obviously, this just means any kind of like rocky material. At different kinds of rocks. You might have learned about igneous rocks. So there's a lot of different types of things that exist on the surface. There's also minerals. So we can learn about if these are kind of useful to us in any way. There's also glasses. Glass has formed on the moon from meteorite impacts, as well as potential volcanic processes. So when a meteor impacted on the moon, it can create like a very high stress, heated up impact, which will melt the rocks around it and cause these glass beads to form. And this is probably the coolest part. I think glass beads are the coolest thing, because you wouldn't expect that to be on the moon. And we've seen glass on Earth, and glass is kind of sharp, but on the moon, it's rounded. It's very, very round. And this is because there's no atmosphere. So if something was to come off of the moon and melt, it would roll and kind of fall back to the moon. And that rolling causes it to become these glass spheres. There's also these things called breccias, which is kind of a conglomeration of rocks and minerals. And then agglutinates, which is like melted pieces of rock and mineral and glass and all of this, which are kind of interesting looking. So we were really interested in looking at the surface of the moon and can we use some kind of engineering solution to help us look at these types of particles through the lens of a computer. So this is a bit of a more in-depth looking at the types of particles on the surface of the moon. Right here is my favorite one, which is the glass spherules. Like, that is so crazy to me that this little ball of glass, these exist on the moon, because I just expect to see gray rocks. But yeah, so something that is really interesting is during the Apollo missions. So in 1969, the first time humans landed on the moon was the Apollo 11 mission. So during the Apollo 11 mission and then the subsequent Apollo 12 mission later in 1969, and then in 1971, the Apollo 14 mission, they had a lot of scientific objectives. They were doing so many different things. One of the things they were doing was taking images of the lunar surface with this thing called the Apollo Lunar Surface Close-Up Camera. And so this camera is handheld. As you can see, it has this kind of like handle, and the astronauts like Neil Armstrong, they literally held it above the surface and took pictures. And this camera is stereoscopic, which means that it has kind of two lenses, kind of like eyes, that take images, and it takes two images that then combined together kind of provides a depth. And it's like a 3D image pretty much. And it allows you to then see what they might have been seeing at a depth and allow you to understand what's going on. So these images are actually available open source by NASA Johnson Space Center and Arizona State University. They combine these and put them open source online. And that was why I was able to take a look at them. But yeah, you can see some of the pictures if you have 3D glasses, and I actually used 3D glasses during my research to actually look at some of these images. You could actually see like this rock is jutting out, and there's these kind of like shiny particles that might be glass or melt or rock. There's like this, shiny thing right here. It's on a rock. And so there's a lot of these cool things that we can see. And this is actually of the lunar surface. And these are they're microscopic images. So actually very close to the surface. So the weird thing about the moon is this looks like this could be a big boulder, but actually it's a kind of a small rock. This is about 8 centimeters by 8 centimeters image. So this rock is probably like 4 centimeters by 4 centimeters. So yeah, it's pretty crazy to think like how the depth and how your perception is skewed when you're looking at pictures of the moon. And it really requires you to have other information to understand. Because on Earth, we have kind of relative points where we're looking at like, okay, a mountain, we can tell it's really tall because we can see a tree and we know how tall a tree is. But on the moon, there's nothing really giving you that perspective. And so it can get really difficult. But yeah, these are some of my favorite pictures. This is my absolute favorite picture. So talking about glass beads, this is an actual glass bead on the surface of the moon that was captured during the Apollo 11 mission in 1969. So I really love this because you can really clearly see the shadow that this glass bead makes and how round and perfect it looks. It's just sitting on top, like you could pick it up. It's a little pearl. And yeah, it'd be really cool to have this pearl, but yeah, it's sitting on the moon and it's probably still there if nothing has touched it or moved it. So yeah, I basically got to look at these really cool pictures for a lot of my masters. And what did I do with these pictures? I used a technique called machine learning. So if you're not aware, machine learning is basically it's a branch of artificial intelligence that helps to understand how computer systems can use data to learn the same way humans learn. So when you're young, you have a certain subset of knowledge. You know who your mom is, you know who your dad is, you know who your friends are, people around you maybe, you know what a cup is, a bowl is. And as you grow up, you learn about a lot of different things around you more in your environment. So this is the same thing with computer systems, that we can show them a bunch of images or show them a lot of data and teach them about different things. And so if you show them a lot of pictures of cats and then you show it a picture of a cat, it could say that is a cat. So this is a very interesting field within engineering to understand how computer systems learn like humans. So very overview. there's this interesting concept of neural networks. And so in your brain, you have neurons which make connections. And that's basically something that can be replicated using mathematics and statistics to replicate that for computer systems. So basically, we wanted to use these really intricate kind of computer systems, which at a high level looks like something like this, where it takes an image as an input of maybe a car, and it feeds it through all these layers. And so your brain has a lot of wrinkles and layers and a lot of things going on. And then it's able to then decide, okay, I've looked at an image of a car. Is it a car? Is it a truck? Is it a van? Is it a bike? And so the computer system is able to take all this information and know what it is looking at, which is kind of a very interesting and cool process. So we wanted to know, can we do this with moon rocks? Like if we were to take a bunch of pictures of moon rocks on the moon, could we train a computer system to learn what a moon rock is and then help us as planetary scientists be able to look through a lot of data at once and be able to understand what's going on? So basically, my job was to take a bunch of those pictures I showed you and feed them to a computer and tell it what each image was, whether it was a glass or a conglomerate of agglutinate or a breccia, and then if it was a melted piece or a rock fragment. So I basically told it what it was. This is what the process called training an algorithm is I tell it what it's looking at. And then the next step is to show it something that I have not told it what it is, and see if it can do the job of understanding what type of rock is present. So this is kind of what the process of me telling it what it is looking at is I would label images. So glass bead, I would tell it this little thing is also a glass bead. Here is a breccia fragment, and then a melt. And the cool thing is I got to work with awesome planetary scientists at Mission Control Space Services, Dr. Moslik Battler and Cassette Gilmore, to help me with this process, because I have an engineering background and a little bit of planetary science background, but they have a lot of planetary science know-how. So they helped me a lot with this process. And then we fed it to the algorithm. We had tons of images like this. And this is kind of how the model performs. So this is my label. I told it in this image, there's some melts. And then in different models, I had different models kind of tell me what it saw. So this model you can see matches with what I initially told it. This model kind of went off book and said, well, I see what you see, but I also see some other stuff. So it's not a perfect system, but it's a very interesting result to see that maybe this system is working pretty well and can see some things that I, even as a human, maybe didn't see. And it's using some of its background knowledge to understand what's going on based on what I've told it. So it's a really interesting problem. There's still a lot of work to do, but it was pretty exciting to see that at least it could do what I told it. And there's some tuning that we have to do to fix it. But yeah, it's so far a very interesting result. So what's next is we actually need a lot more data. So a really interesting thing about machine learning is that you need a ton of data to do this task. Just like humans, we absorb a lot of information every single day, every single minute. Computers need a lot of information to help them learn and understand what is and what isn't existing and what they're looking at. So there's a lot of cool lunar missions actually planned for this next decade. We're hoping that we'll get more data, that images will be coming, rovers will be going, and pictures will be taken. And so with more data, we'll be able to teach these algorithms and train other algorithms to do the tasks that we want them to do. And speaking of other lunar missions, now I can show you some cool pictures. Is I actually, at Mission Control, I got to go in a couple times. I actually got to meet the astronaut who's going around the moon on the Artemis 2 mission later this year, Jeremy Hansen. And so the cool thing about Mission Control is they have this moon yard in their office, literally behind one door. They just have a replica of what the moon could look like. And so Jeremy had come to the office, and yeah, we took a picture of an astronaut on the moon yard, which I thought was really funny. So yeah, it was really cool to get to meet an actual astronaut. Working in space is a really fun job. You get to meet a lot of cool people. And also these other people in this picture, you know, at Mission Control, they're also very cool. Everyone who works there is very cool. So that's everything about moon rocks and what I did in my research. Now I actually work at a company called Planet, as I mentioned, and I get to work on satellites. And I did an internship with them a couple of years ago, and now I'm back working on operating the satellites. But I used to get to build satellites. So this is a picture of me with the team after we finished building about 49 satellites, which is a pretty big feat. And this is kind of how big the satellite is and what it looks like. I actually got to put some art on the satellites. So I got to make an image and they laser printed it onto the side of the satellite. Now the satellite is actually in space. And so my art is flying in space. So that's pretty cool. But yeah, I'd love to talk to you more about kind of what I do in my day-to-day at another time. But yeah, that's pretty much everything about what I've been doing. And yeah.
Fantastic. Hira, there's so many things in that. By the way, you mentioned a few organizations throughout the course of that. Planet.com, Mission Control Space Services. We featured them in Vanessa Van Dekker's presentation. And of course, space.uwo.ca. Just a big shout out to the amazing organizations that you've been involved with and that are behind our program today. And thank you so much for highlighting moon formation, one of the coolest things in the history of science ever. Like the fact that like a chunk of the Earth was blown off and like reformed as like this like lava blood moon with the way closer to us too. It was like the most metal time in the history of the solar system. It was very cool. So, thank you for all of that. And we're going to dive in with questions. Our Raymond, Alberta crew, 5-6A, Miss Gold's class. I'm coming to you all in a minute. YouTubers, you can share in the chat if you'd like. We'd love to hear questions from you as well. But I'll start with, for our students in grade 6 today, who might want to go on to be space engineers and put art into space on satellites and do all this cool stuff you've had the chance to do, is there a recommendation of what they should be focusing on in school or taking at this moment to best have a best chance?
Yeah, so I mean, if you're in grade 6, I think you have a lot of time to figure it out. And I think the best thing about the space industry right now is people with different backgrounds, not just engineering, not just science, can actually get involved in space. So
yes, I'm so glad you mentioned this. So this is something that NASA people and Canadian Space Agency people say all the time. Like I think we all assume astronaut. We assume Jeremy Hansen. But if you're in business, if you're in finance, if you're in art, if you're in communications, I mean, there's a million jobs in the space sector. So you can be involved in something like a moon mission, which is literally happening again right now for the first time in decades, which is so exciting. I say every time we have a space person on, it's like the most exciting time to be ever interested in space. If you're in grade 6 right now, you're of the age that will be like the group that will go to Mars.
Yeah.
Wild to think about. We've been talking about it for so long, and like the plans are in motion now. So it's keep gaining more skills. The more knowledge, the better, and have that level of enthusiasm, and you can be like Hira. And yeah, it's very exciting. Our Raymond, Alberta crew, I'm going to come to you, grade 6s. If you guys want to kick us off with a question, you are in the broadcast and good to go. Hi, guys. Hey. Does anyone have a question for Hira today? Oh, thinking about it. No, that's okay. I can come back to you if you do. We'll go to our 5-6A crew. If you guys have one for us, you can unmute your mic and come on in. Hi, guys.
Hi, perfect. We do have a question. Muzaki, come on up.
When you look at like the stereoscopic images, do you feel like that's like a stop motion pictures or something like a movie?
Interesting question.
Yeah, so not exactly, because they are just still images. They are, one image, but I have seen cool compilations of people putting them together and showing us like the back and forth between the two lenses rather than just the 3D image. And I think those are really cool because you can still see the depth when you flip back and forth. But yeah, I think like you could make a lot of creative things with these images and even make a stop motion of the lunar images as well.
I'm so happy you mentioned the art aspect, because it's been something we've actually been hearing in our last few space programs. We went years when people didn't mention any things that they were doing on the side with it, and it's so important. Artistic people in general tend to do better in science. This is something that I've found anecdotally over 1,500 broadcasts now, is that approach and the way of viewing the world helps make you better when you're doing the creative work of science. And so I'm glad we got that question. Thanks, guys. Miss Goet's class, grade 3s, I know you're a virtual school, so I'm going to come to you. If you have a question for us on behalf of your class, welcome to the broadcast. Hey.
Hi there. I know this wasn't directly but one of my students was just wondering a kind of a general question about whether, like,
Please.
how fast it would take. What's the fastest that an astronaut has gone to the moon? What's their question?
Fastest we've ever been to the moon.
I know that's not specific to you, but sorry.
Yeah, I mean, from what I remember, I think it does take a couple days, and I think that's mostly just because there were a lot of safety in place and a lot of different physics around actually landing on the moon. So I think it is still a couple days, even now with Artemis. Though maybe with shuttle they were able to get a bit faster after the initial moon landing. But I would imagine that it's going to get quicker as they do more of these landings. And to be honest, I think. I think it's an exciting time.
I also love the fact that by mentioning a couple days, like people always, we hear from kids regularly, like, why not just go to Mars? Why didn't we go to Mars? So the moon is a few days and Mars is many months. Like it's like a 6 month to 1 year plus, like there and back journey. Yeah. And so it's such a different order of magnitude for a challenge. It's why we haven't gone. It's why there's been so much research and development and how we can even live in space that long over the last few decades to prepare us for something like that.
Yeah.
So thank you for that question.
I think to add to that too, the cool thing is about communication going to the moon. So if we send a signal to the moon, it takes a couple minutes actually. And then even to Mars, there's a delay. So even when we're communicating, getting to the moon, the fastest we can talk to the moon is even a couple minutes.
Yep. Very cool. Thanks, guys. All right. Grade 6 Raymond, you have some students at the camera now, so I'll come back. Welcome in.
All right, go ahead.
Hey.
How expensive would the glass bead be?
Oof. I feel like it would be pretty priceless if there's only one that they were able to bring back from the moon. I think they would probably put that in a museum, but I think there's a lot of glass beads on the moon, and if they were able to bring a bunch of them back, I think that would affect the price. But I think I would pay some good money to get a glass bead. How cool would that be?
It's pretty cool. I will say, so when the Apollo astronauts, the missions that went to the moon, the 6 missions that landed on the moon, brought back a total of a little under 900 pounds of moon rock. So there's not that much that we've ever extracted from the moon. Most moon rock on Earth actually comes from meteorites, hit the moon, which is, by the way, so right up there with moon formation. So a meteorite hits the moon, blasts off a chunk of the moon, and that comes to Earth as a meteorite of itself, and that's moon rock, and we can identify that on Earth is like black magic and super, super cool. But like if you were to go to the moon and get like a special bit of volcanic stuff and bring it back, most expensive jewelry of all time. Hope Diamond has nothing on moon jewelry. That's very, there's our future. Great question, guys. 5-6A, I'm coming back to you. We're going to do another round of questions. YouTubers, feel free to chime in as well. But come on back in and alcohol. Bye, guys.
Do I have to like call them?
Come on up. More fun that way. Hey.
So, images taken from telescopes like the Hubble telescope, they're actually what happened thousands of years ago, right? Because they're thousands of light years away.
Yeah.
Do we have a way of calculating what that would look like now?
Ooh, do we have a way of understanding what things that like the Hubble telescope or James Webb Space Telescope are looking at are like at this moment?
I think so. I'm honestly not an astronomer, and I think honestly what they do is so amazing. But I think that the time scale is still pretty small. So even though we took images from Hubble like maybe a couple decades ago, that time scale of that light reaching us from those galaxies, those distant stars, it's still pretty, like 10 years is pretty small. So they look pretty much the same as they did when we took them initially.
So if we go further back in time, something like if we're looking at something that's close. So right on, student, by the way, like if you look at something that's 10 light years away, just for students that might not know this idea, we're seeing that thing in the past. The telescope's literally a time machine because the light has taken 10 years to get to us. When you go into the cosmos, the scale becomes really hard to envision in your mind. There's no way that people can naturally think about this. If you look at something that's 10,000 light years in the past, you're not seeing that as it exists now. That star could be dead. It could have blown up 5,000 years ago, and we'll still see it in the sky, alive, quote unquote, for thousands of years after because the light hasn't reached us yet. it's really, you get into the weeds of space exploration. It depends on how far back you are. But yes, early Hubble telescope images will have seen something from decades ago, and that will be what it is now, basically, because we were looking at something from 20 light years away. It's been in the sky for 20 years. We can go, oh, that's what it actually looked like back when we were originally looking at it. But something that's like a million light years away, we'll never see that as it exists. Like we're seeing it from a million years in the past. We could go into the weeds in this very fast. It's crazy, and it's very fun.
Unless we go, and to go there, who knows?
We're going super sci-fi now. Who needs Mars when we can go to other
like super fast and go back in time?
Fantastic, here. I like the ambition. Miss Goad's group, I'm coming back to you, and then our Raymond class. I'll wrap up with you guys right after that. Hey, Miss Goad.
They're talking more like astronaut kind of questions, like wondering how much fuel it would take, but that's kind of not what you were presenting. So
I like that they're so keen. Hira,
I know, I don't know myself. Yeah.
So do we know, actually, Hira, I know it isn't your area of expertise, how much fuel it takes or how difficult it is to actually get a rocket to something like the moon?
It's a lot. I actually have a little mock-up of the Artemis rocket. So this took so many years, so many decades to develop, and the amount of fuel, I think, is pretty significant. I actually don't know the exact, but it's a lot.
So the Space Launch System is what we're using now. It's the biggest rocket ever, to my knowledge. Saturn V is what we use to get to the moon. And for kids that ever get the chance, if you ever go to Cape Canaveral in Florida, you can see a Saturn V on its side and see the scale of those rockets.
Yeah.
It's like your entire year for a car in like a second. Like the rockets are absurdly powerful because they've got to lift millions of pounds off the Earth and to the moon. Like it's space is cool. I told you, it's the best time to be ever interested in space.
It really is.
I'm glad we got that question. Alberta class, I'm going to come back to you guys and we'll wrap up after that. I will note again, if people want to learn more about Hira's work, if you want to get excited about space generally, NASA, the Canadian Space Agency, both have incredible websites to learn more. Space.uwo.ca is behind this entire broadcast series, and they've got a ton. Western in London, Ontario, is doing some of the coolest cutting edge research on space. In fact, for our classes that are in Southern Ontario, there are so many opportunities here if you want to end up with a future in space. My brother-in-law is going into a future in space, and right here in the province, because there's that much going on. So you can go to San Fran though, like here, it's super cool. It's very fun. Grade 6s, Raymond, come on back in and take us away. Hi.
Can we do 2? Is that okay?
Yeah, of course.
Come on, guys.
Hey.
I was wondering, how much of school do you need for the job to build the satellites?
Ooh.
Oh yeah. I mean, like, honestly, the cool thing about satellites, especially cube satellites these days, is that you don't need to be like a rocket scientist or a satellite scientist to build them. I've actually heard of students, even your age, who have developed satellites that are going into space. And a lot of it is becoming commercial. So companies have developed different things. They don't have to reinvent the wheel, and you can put them together. And the thing that you really have to focus on is your payload or the scientific instrument that you're trying to use. And so some of the CubeSats that I've worked on, they have, I worked on 2 with the Canadian Space Agency. One just launched just a month ago, and just deployed. And that does like radiation detection in space. And then one is launching soon. That's just a camera, 360-degree camera that will take images of the Earth and space at the same time. And so if you have a really interesting idea about doing something in space, you know, the work to get there, it really takes a big team, and you can do it at really any stage at this point with CubeSats.
We've actually had people on in high school that have talked about doing CubeSat projects. So like in a few years, kids, if you're keen on getting satellites into space, you can actually work on those projects. I just shared the Canadian Space Agency link for CubeSats. Let's Talk Science is a spectacular organization that's done things with Tomatosphere and CubeSats in the past as well. So some really cool opportunities. And just generally, one thing that I always like to highlight when we get school questions before I come back to you guys and Raymond is you're in grade 6. And the thought of going to grade 12 and then doing an undergraduate degree for 4 years and then a master's degree and maybe a PhD is like daunting and insane. It sounds like so much school. But whatever level you do, here is like, yeah, I just did my thesis. Whatever you do, you end that and you're really young, and now you get a dream job. You get to play for your work for the rest of your life and work with amazing people and go to amazing places and do exactly what you love, and quite often for quite a bit of money too, for good measure. So like doing that amount of school, if that's your interest, is a really rewarding thing. We have the pleasure on this broadcast of featuring so many scientists and explorers around the world, and we've never had anyone that said, you know, it really wasn't worth it. You put in that effort early on if you're committed and passionate about something, and it can really change your life and make your entire life extraordinary. So,
and to add, like, it really depends. Like Jesse said, it's like, what is your interest? I didn't have to do a master's to do the job that I'm doing now, but I did a master's because I was really interested in like exploration and moon and stuff like that, which I didn't just get from engineering. But you could do like a different degree, and then if you did a project that's hands-on, like really getting experience and learning hands-on is the key here. So yeah, if you get that experience, you don't need to just rely on your education. It's kind of the combination of doing that.
Whatever you're keen on, if you reach out to astronauts or the space agency or whatever and say, I love this, I'd love to help out, 9 times out of 10 people will be like, come and meet us and let's figure out how you can do that. We don't bite in the science community. We're like really excited when people are super keen. So I'll stop there and go back to Raymond for one final question, and then we'll be bringing in everyone to say a big thank you and farewell after that. But wrap us up with a last question. Hi.
How long does it normally take to build a satellite?
Oh, yeah. So this definitely can range. So like I mentioned, I did an internship at Planet a couple of years ago, and that's a big team. They have all of their facilities in-house. So they have like, you know, from the ground up, like the board level, all the way up to the actual physical satellite. They do all that in-house. And so it can take like almost no time. So they built 49 satellites in like less than a year, like a few months actually. And then, you know, you look at other projects that I've worked on with smaller teams, with student teams, where we're learning as we go, and we've never done this before. It can take a couple of years. So even the one that's launching coming up, it's taken about like 5 years. That's also exacerbated by the pandemic. You know, it took some time out of us being able to work on it, but it can take a really long time. And the best thing, as mentioned, CubeSats, the best thing about these things is that it used to take like decades to develop satellites that went on to do science around Earth or beyond. And now it actually can take much less time. And it's just like continuously doing it. And the quicker they do it now, like some CubeSats I've heard of being done in a couple months at some companies.
The moral of this story is that, like our Raymond Alberta class, you guys can start making a CubeSat like right now. We're going to get it into space very fast. Classes, this is so much fun. Hira, your enthusiasm is palpable. I can't believe you're this energetic this early in the morning. I'm like a zombie with coffee at this point. So a huge thank you for joining us after a really big day for you, and a huge congratulations on that. Classes in Ontario, Alberta, the United States, and beyond. It's such a pleasure having you in to learn about all this. Again, check out our series at space.uwo.ca. This program, like all our others, will be on our YouTube channel if you want to check it out and share with people after the fact. And here, what we do to wrap up every broadcast, I'm going to bring in our classes to say a big thank you and farewell. Raymond Alberta, 5-6A, Aberfoyle, if you guys want to unmute your mics, you are good to join me. Thank you so much, everyone. Have a wonderful day. Bye for now, guys. Thank you so much.